The first thing that you should do for signal integrity applications after opening HFSS is check to see what solution type HFSS is in. Typically, you want to be in driven terminal mode for signal integrity applications. Drawing bond wires in HFSS is exactly the same as drawing them in Q3D. In order to do that, you can go to the Draw menu, Bond Wire, and then select the start and end points of your bond wire. Click once and click twice, and then the JDEC 4-point or 5-point standard will pop up in which you can add the dimensions. In this case, I'll make the H2 0.1 millimeters and click OK. You can add a second bond wire by again going to Draw and clicking twice. And we'll make that one the same dimensions. The setup is a little bit different than Q3D. Instead of placing sources and sinks on the faces in which the current goes in, we need to define ports. And the easiest way to do that is to use a lumped gap port, in which we first need to define a reference plane in which we're going to be drawing the current for that port. And an easy way of doing that is by defining a sheet object underneath the ends of the bond wires. So it's kind of like a bond pad for the reference plane. In this case, I can put it into a top-down view by holding down Alt and double-clicking on the top of the screen. I want to draw a rectangle around the ends of the bond wires. And I'll do the same thing on the other side. It doesn't really matter too much what your size is of this, because it's just going to serve as an ideal reference plane for that bond wire. And when I drew that, if I rotate it, you can see that it's not at the correct levels that I want, but that's okay, because I can go back and change that by editing the project tree. So the two sheets that I just defined, rectangle 1 and 2, if I click on that, I can see it's there. And I want to define this slightly below the ends of the bond wire. So if I double click on Create Rectangle, I can see my Z position there. If I make that negative 0.02 millimeters, hit OK, now when I rotate and zoom in, I can see that that plane is slightly below the ends of the bond wires. And I'll click on the second one. If I double click on Create Rectangle, I want to place this one below the ends of the bond wire. And I knew that H1 was negative 0.1 millimeters, so I'll make that negative 0.12 in order to make it slightly below. And again, you can see it is below those bond wires. I also need to define my materials, what I'm going to make the bond wires. So if I select both of them, I can edit the properties of this. By default, everything that you draw in HFSS is going to be a vacuum. But in this case, I want to make it gold. You can also change the color just to help identify the different objects. And these two sheets that I drew, I'd like to make those an ideal conductor. So I can just assign a perfect E boundary to them. So if I right click after selecting them, do Assign Boundary, and do Perfect E, and click OK. And let's make those green as well so we can identify them as ground. So now that I have my geometry all defined, I can draw in the lumped gap ports. In order to do that, I can zoom into the area where I want to make the connection between the bond wire and the reference plane. And I want to draw a 2D sheet. So I can select the 2D sheet, and now I can define which area, which plane I want to draw that in. And since I'm going to be going from top to bottom, I can define it in the YZ plane. And you can see that the grid changes behind. I also can change the different snap modes that I have here. And I want to turn off the grid snap and leave everything else on. So when I come close to some of the geometry, you can see how the cursor changes. It's actually finding a snap point for the beginning of that 2D sheet. So for this, I can snap here on the end of the Bondwire, and you see I have full flexibility. I want to be able to place this Bondwire somewhere in between the ends of the Bondwire. So as I'm moving across in the Y direction, if I hold down Control and then click, I've basically defined the width that I want. I now want to make this the correct distance in the Z direction, so I can snap to one of the corners of this plane that I defined. So if I hold down Z, I can find the corner and then click the mouse again and see that I've defined the start, the midpoint, and also the distance by holding down that Z button. I can now assign a lumped gap terminal by right-clicking and doing Assign Excitation Lumped Port. I can then select which is the conducting object and which is the reference conductor. And rectangle 1 is going to be the reference conductor, so I can move that over there and click OK. And see the excitations we just defined our lumped port in the project tree. I can then move over to my second Bondwire and do the same thing. Click the rectangle, define my start point, go some distance over, click Control, click again, and then hold down Z and click the corner of this sheet. You can right click, assign excitation lumped port. And we see that we've already defined rectangle 1 to be a reference, so HFSS can remember that. On the far side, we want to do exactly the same thing. Assign one edge, go over some distance, hold down Control, click the mouse, you can zoom out and hold down Z and we'll find that corner again and click. Right click, assign excitation lumped port, and the final Bondwire. And it's always important to visually inspect where you've drawn your rectangles to make sure that they are making contact where you expect them to. Another important difference between HFSS and Q3D is that by default the background material in HFSS is solid metal. And so since Bondwires obviously are not going to be engulfed in metal, we need to define a region around this in which we can specify the material to be a vacuum or a molding material. So this can be done automatically by clicking Draw Region. We can give padding in all directions. Let's do 50% padding in all directions and click OK. And you see that a box is automatically defined around here with the material of vacuum. The way we have it defined right now, this is essentially an air pocket in a vast source of metal. But we can assign a boundary condition to this to mimic the effects of being an infinitely large vacuum. In order to do that, we can select that region, right-click, assign boundary, and do radiation boundary. And click OK. And so now any energy that reaches that boundary will hopefully be absorbed and mimic the effects of an infinitely large space. And if we don't care to see this, we can select that and click the little icon of the eye with the X through it, and we'll hide the visibility of that. So now it comes time to defining the sweep. So under Analysis, if we right-click, we can do Add Solution Setup. And here we want to define the maximum frequency that we're interested in. In this case, we'll make it 5 gigahertz. And typically the defaults are usually OK. And click OK. Under the setup, we want to define exactly which frequencies we want to include in that sweep. So we can right-click and do Add Frequency Sweep. And here we can define what type of sweep we want. For signal integrity, usually an interpolating sweep down to DC is preferred. So you can put in a start frequency of 0, a stop frequency of 5 gigahertz, and for speed, let's just make it 100 megahertz steps. And if we click Extrapolate to DC, we can hit Display. And click OK. And we should be ready to go. If we click on the checkbox up here, we'll analyze our entire project and it will tell you whether or not everything was set up correctly. In order to analyze it, we can click the exclamation point. And it's done. To view the results, if we right-click on the results menu, we can do Create Terminal Solution Data Report. Click Rectangular Plot, and here we have all of the S parameter data that was just solved for. So if we're looking at some of the S parameters, we can plot the return loss as well as the insertion loss. Click Add Trace. And we can see the total loss in our system from 0 to 5 gigahertz. If we wanted to export this data, we can go to the setup, right-click, and click Matrix Data. We can select all frequencies, and we can export matrix data in which we can save a touchstone file of all of this frequency domain data.